Hello, welcome to today's mini lecture on how to solve polynomial equations of degree 3 and 4. These are equations of the type 2x cubed plus 5x squared minus 11x minus 21 equals 0, for instance, or 2x to the power of 4 plus 3x cubed minus 16x squared plus 21 equals 0. You hopefully remember that those with degree 2 quadratic equations can be solved with the infamous quadratic formula. They have 0 or 2 real solutions, and in rare cases only one, a so-called double zero. Cubic equations have 1, 2 or 3 real zeros. However, the case of 2 real zeros is rare. It is kind of a special case. Quartic equations have 0, 1, 2, 3 or 4 real zeros, but here the cases of 1 or 3 real zeros are rare. And yes, there is a cubic formula and a quartic formula, where similar to the quadratic formula, the solutions can be calculated from the coefficients of the equation. They have been found and published by Tartaglia and Cardano between 1535 and 1545. This is a nice story, why don't you Google it? However, these formulas are complicated and use complex numbers, even if the solutions are real, so we will not discuss these formulas here. Maybe in another mini lecture. The 21st century has a very convenient method for solving any equation. All we need is a good graph of the function f if the equation in question is f of x equals 0. The x-intercepts of that graph are our solutions. Take the example 2x cubed plus 5x squared minus 11x minus 21 equals 0. The graph of the function f of x equals 2x cubed plus 5x squared minus 11x minus 21 is shown here, and has obviously 3 intercepts. The function has 3 zeros, the equation has 3 solutions. One around x equals negative 3, one around x equals negative 1.5, and one around x equals 2. Easy, isn't it? We just have to make sure that we don't miss solutions to the left and right. So, case settled, class dismissed. Except for those of you who feel that even though we have cars and using a car is the fastest and most convenient way to go to school 3 kilometers away, if we are healthy, we should also be able to walk such a distance. We should even be able to run that distance, don't you think? Exercising is healthy. In the same way, brain exercising is healthy. We should be able to solve cubic equations without using a computer. Just because we are humans, an intelligent species.
Please, enough of this Boy Scout pep talk. Just go on with the lecture, will you?
And of course, as a second reason why the graphing method is maybe not sufficient, looking at the graph gives us only approximations of the solutions. We may want to express the solutions precisely. So let me show you a method which could be described as: if you can guess one solution of a cubic equation, you can find the others too, if there are any. And guessing is maybe not a good word for a proud, intelligent human being. Let's rather call it educated guessing. Or let's even call the method confidently: if a cubic equation has at least one rational solution, then we can find all real solutions, rational or not. What we need first for the educated guessing is a so-called rational zero theorem. It says that if a polynomial equation with integer coefficients has rational solutions, then these rational solutions are among a finite list of candidates. The candidates are all fractions a over b, with a factor of the last coefficient of the polynomial and b a factor of the first coefficient, provided the terms are ordered from high exponents to low exponents. In our example, the first coefficient is 2 and the last coefficient is negative 21. The divisors of negative 21 are plus minus 1, 3, 7 and 21. The divisors of 2 are plus minus 1 and 2. Therefore, we get the following candidates: plus minus 1 over 1, plus minus 3 over 1, plus minus 7 over 1, plus minus 21 over 1, and plus minus 1 over 2, plus minus 3 over 2, plus minus 7 over 2, and plus minus 21 over 2. After producing this list, all we have to do is to check which one of the candidates is really a solution. Intelligent species or not, we might not be exactly thrilled to check 16 different candidates for 0. It is easy, yes, but it is not challenging, it is boring. Even though exercise is good for us, rather than walking for 2 hours in the city, with maybe heavy traffic, it might be wiser, even healthier, to take the car and drive to the park and run there. So it might be wiser and healthier to allow us to look at the computer-generated graph above and to notice that there is a rational 0 at negative 3 over 2. After having found one solution, what about the others? Remember that if a number a is a solution of a polynomial equation, then x minus a must be a factor of the polynomial. In our example, x minus negative 3 over 2. X plus 3 over 2 must be a factor of the polynomial, 2x cubed plus 5x squared minus 11x minus 21. Thus, x plus 3 over 2 times another unknown polynomial equals 2x cubed plus 5x squared minus 11x minus 21. In other words, the other unknown polynomial is a quotient of this 2x cubed plus 5x squared minus 11x minus 21 and x plus 3 over 2. This quotient can be found using long division. We get 2 times x plus 3 over 2 times x squared plus x minus 7 equals 2x cubed plus 5x squared minus 11x minus 21. This product is equal to 0 if one of the factors is equal to 0. So if either x plus 3 over 2 is 0, meaning x equals negative 3 over 2, or if x squared plus x minus 7 equals 0, but this can be solved using the quadratic formula. We get x equals negative 1 plus minus square root of 1 minus 4 times 1 times negative 7, all that divided by 2, which is equal to negative 1 plus minus square root of 29 over 2. So these are the remaining two solutions. Here's a general procedure. Number 1, find one rational solution, if there is one, A, using the rational zero theorem. 2. Write the given polynomial as a product of x minus 1 and the quadratic polynomial using long division. And 3. Find the solutions of this quadratic polynomial using quadratic formula. For quartic equations you can use essentially the same method. We try to find one solution, then factor and get a cubic equation, which we may or may not be able to solve using the method discussed above. There is another reason for using the method described instead of just graphing the function. Sometimes we don't have just an equation, but a whole family of equations with a parameter k, like 2x cubed plus 2k minus 3 times x squared minus 5k times x plus 3k equals 0. So k is a parameter. That means that for every fixed value k, we get the corresponding equation. Using graphs, we can approximately solve the equations for any single k, but in order to solve it for all k, we need our method. Below the graphs of a few of these functions fk of x equals 2x cubed plus 2k minus 3 times x squared minus 5k times x plus 3k are given. Note that they all have a common point at x equals 3 over 2. And note that the value fk of 3 over 2 equals 2 times 3 over 2 cubed plus 2k minus 3 times 3 over 2 squared minus 5k times 3 over 2 plus 3k, which is equal to 27 over 4 plus 18k minus 27 over 4 minus 15k over 2 plus 3k, which is equal to 0. So 1, 0 was easy. It is x equals 3 over 2 for every k. Polynomial division of the cubic equation with parameter by x minus 3 over 2 yields 2x cubed plus 2k minus 3 times x squared minus 5kx plus 3k equals x minus 3 over 2 times x squared plus kx minus k. And according to the quadratic formula, the zeros of x squared plus kx minus k are x equals negative k plus minus square root of k squared minus 4 times 1 times negative k all divided by 2, which is negative k plus minus square root of k squared plus 4k divided by 2. Thus the equation 2x cubed plus 2k minus 3 times x squared minus 5k times x plus 3k equals 0 has three real solutions: 3 over 2, negative k plus square root of k squared plus 4k divided by 2, and x equals negative k minus square root of k squared plus 4k all divided by 2. Thank you for your attention.